In the last lesson, I hooked up 20 LEDs to an STM32 L4 nuclear board, and I wrote this code to turn them on. However, I said this is not necessarily the most efficient way to address registers, and on this video, I'll show you how it's actually done in the field. If you want to watch that video, click that link on the top right. Otherwise, let's dive in. In this code, we're addressing every single register, and a lot of the values here are hard-coded, which is not desirable. As a developer, you don't want to go trace down all the register offsets and try calculating all the addresses. A better way of doing it is through structured pointers. It saves us time, it's more mistake-proof, and our code looks much cleaner. So I'm going to show you how it's done for this first register, and pretty much every other register follows the same principle. So if you remember, we hard-coded this value for RCC base, and then we calculated address for this particular register using RCC base and the register offset. So we don't need any of this code. We're going to comment these out, and instead we're going to build our address. Instead we're going to build our addressing from the beginning. Since we're addressing peripherals, we need to go get peripheral address, where all the peripherals start. Peripheral base address. So to do that, we need to look at the memory map again, and we're gonna see peripheral start here, and the address that they start at is this address here, 4 and 7 zeros. So we're gonna copy that and come over here. We're gonna do define. I'm gonna define peripheral base. So we'll go right underscore base, and then we'll paste that value right here. It's also good to put UL at the end. This signifies this is unsigned long integer. Alright, now we have peripheral base. That's where everything starts for us. Now we need to go find out where this RCC is. And from peripheral base, we'll go look at our buses and find out what bus bases are there. So since we're interested in RCC, we're gonna go find out what bus RCC is sitting on. So we're in the reference manual. We're gonna scroll down and find RCC, and here's the RCC. Great. RCC is part of this AHB1, which is Advanced High Performance Bus 1. And beginning address, you would have to look in the bottom here. So this is the lower address and the higher address up here. So the lower address, beginning address of AHB1 is this one here. So we're gonna grab that. We don't actually need all of it, but we're gonna grab it and bring it over to our code. And over here we're gonna do define, and this time we're gonna define HB1 peripheral base. What we were looking for is this. So we need this address. This is the base address for AHB1, but we don't want to hard code this, because we want things to be more dynamic, because we'll be reusing peripheral base, we'll be reusing AHB1, and even we'll be actually making AHB2 and so forth. So we want everything to stay dynamic, and we don't want to hard code anything. So over here, you're going to see this is the actual offset. That's the only thing that's different on this from peripheral base. So what we need peripheral base plus this offset right here. And that's hexadecimal. There we go. I will make sure this unsigned long integer. Let's do a little bit of formatting here so everything is nicely aligned for readability. So great, we have HB1 peripheral base. Okay, where do we go from here? So we're interested in RCC, so we need to go define RCC base. In fact, the exact address here of RCC base is defined above, hard-coded, but we want to arrive at that same address base dynamically. So we're going to need to, let's copy this. So we're going to need define RCC base again. And to define this, we of course need HB1 peripheral base. And then we're going to add the offset, which is actually right here, 1 and 3 zeros. And that's in hexadecimal. So we'll do 0x, 1, 3 zeros, UL. Okay, and that's actually going to bring us to this address right here. Perfect. So now we have RCC base, and all the registers are here in RCC base. Now we need to go find our individual addresses. So if you remember, we used to go and look for all the offsets for every single register. We don't need to do that. There's a better way. So we're going to create a structure that holds all the RCC registers. So let's do that. So what we'll do is type definition struct. We're going to create a structure. Let's call this RCC underscore type def. Okay. So now we're going to list all of our registers inside the structure. And obviously, we need volatile keyword. Volatile keyword helps us to make sure that hardware doesn't change the contents of this variable. We want to make sure that we always get the value of the register from the hardware itself. So no optimization needed. All of the registers, for the most part, in STM32 are 32-bit registers. So we're gonna go uint 32, and the first register, let's go see what's the first register in RCC. For that, we need to scroll down to RCC registers, and first register is actually the CR, which is clock control register. So we need to say CR semicolon. Here's our first one. Then we'll do another one. What's the second one? Let's see, second register is this one, ICSCR. So I'm gonna fill all out offline and then come back when I'm done. All right, I'm back and I have all the registers here listed. All of our registers for RCC. We don't necessarily need all of them in this code, but in the future code, you may need them. So it's good to have them all. So what we need to do now is we need to turn RCC base into a pointer like we did over here, as you can see. But we're not going to turn into a U32 pointer. We're going to turn it into structure pointer. So we're going to cast this RCC base into the structure as a pointer. Let's do that. So we're going to call RCC. This will be named RCC. And now, so we're going to grab RCC base. We want our compiler to think that RCC base is a structure pointer that points to the structure. Pointer needs a star. We have a RCC is now a structure pointer. And when we access the members of the structure, it will give us exact offset for a given register. We don't need to calculate it ourselves. Here's how we'll do it. So we're going to comment this out. We don't need this. So we're going to grab RCC. And we're going to do structure pointer operator like this. And look at this. When we do that, the IDE already knows that we have a structure. So it actually helps us to see our registers. And as you can see, the one we need is this one, AHB2 enable register. Perfect. You click on it and it's there. And the rest of the code is actually the same. We're going to put the same value. We're going to modify this in the future because we want it to be more like a mask. But for now, that's what we need. Perfect. Look at this. Now let me compile this. I'm going to compile this, so make sure it compiles. Let me pull out this here. Looks like we did not have any errors or warnings. Perfect. Now next, we're going to test this on the board to make sure those LEDs turn on. All right, I have the board hooked up and I started debugging. So let's step through it. The first line of code is the one we just wrote. Go through mode R. And now these two lines of code, 124, line 124 and 127, those are the ones that are turning on our LEDs. So we're going to step through them as well. And indeed, the LEDs came on. Now this is great. Our code actually works. Our LEDs turned on. And the RCC registers are addressed the way they're supposed to. And we didn't have to go find out specific offset for AHB2 enable register. Structure pointers are a common way to address registers in an STM32 microcontroller, and this is what we'll be using throughout the course. Now you might be wondering, will we be typing all these registers for every single peripheral in our code? I have a good news for you. No, you don't have to, unless you really want to. So there is no need to reinvent the wheel, because somewhere has already done all that typing, so we don't have to. So all we need to do is actually include this header file in our project. So this header file is for STM32L432 microcontroller, the one that I'm using. So if we scroll through this header file that I have, we'll find all those structures and structure pointers. For example, this one's for ADC. So we don't really need to type any of this in. All we need to do to include this one. And there are a few other STM header files that we need to include in our project. And I'll put links in the description to all those files. So next, we're going to remove all this code that we just typed in because we don't need that. Everything is included in that header file that I just showed you. And we're going to include that header file in our project. And the execution of our code actually shouldn't change. All this information here on line 111 should stay the same. And after that, I'm going to modify the rest of the registers in the exact way we did for this one. All right, so now I'm going to go ahead and delete some of the code that we wrote because we're not going to need it. We're going to use the header files that are provided to us by ST Microelectronics. So go ahead, delete all this, and also go ahead and delete all this. You actually don't even need this one for now. In the future, you may need if you're using standard integer types in your main function, but for now, we do not need it. All right, next we're going to go to our project folder. And by the way, if you don't know how to create a project, empty project, it's actually very simple. Go to File, then go to Project, Create, Import. And over here, choose this one here, create. You'll be creating STM32 Cube IDE empty project, and click Next. And then you'll be brought to this page where you can select your MCU or your board. I like to go with the board because it's easier. And here you can search, for example, I search Nucleo-L432. So this is my board, and you click on it, and you click Next, and then you give a project name, and then you click Finish, and it will create for you an empty project. So let's get back to code. Okay, next we need to include our header files for our code to work. So before we do that, we're gonna actually comment these out, these GPIO ones, because they will not work because they're not done in the way that RCC is done. Next, I'm gonna grab my header file that I just downloaded. I'm gonna drop it inside include. Okay, once I have it there, I'm gonna include this. Okay, and then I'm gonna compile. Okay, so project did not build because we're lacking a few more header files, because this STM32L4 header file is referring to few other files that need to be included in our project. Actually, if you come to this error and you double click on it, it will bring you to that place, and we need a few more files which I have already downloaded, and I'm gonna put all the links in the description below so you can go and download those from ST Microelectronics GitHub page. And if your STM32 microcontroller is different, you can probably go to the top file in ST microcontroller GitHub page and search it there. Or you can just do a Google search for your files, for your header files, and you should be able to find them. And if you're having trouble, just leave some comments below and I'll try to take a look at them as soon as I can. So anyway, I'm gonna bring rest of the files that I've downloaded and we'll build again. Okay, here are my files that I downloaded, and these are mostly header files filled with definitions, and at some point we'll go and explore to see what's in them, but these should not really hinder us from building bare metal code. And now when I hit build, it actually built, so all good. So what I'm going to do is I'm going to rewrite those GPIO registers in the same way we did RCC, and then we're gonna run it on our board. All right, let's see here. So let me actually uncomment all of these. This is exciting. We're doing this the right way. So I believe, let's see, GPIO A, if I did a pointer like this, yes, as you can see, when we do GPIO A and the structure pointer, it actually gives us those options. So we have these options here. These are all the GPIO registers. So great, we'll just do the same. Just grab this, take this tab out, put the arrow, okay? And if we didn't have mode R, for example, we could just do this structure pointer and it will reveal those registers for us. We'll just go to mode R and hit enter. So I'm just gonna save us time, just go and do arrows like this, and same thing for bit set and reset. Look at that. Now this code is much easier. It's much easier to read, it's much easier to maintain. You can actually come over here, so hover on mode R and hold down control, and then you click on it, and it will bring you exactly to that GPIO type definition. So we don't need to retype all this. So ST Microelectronics already done that. So, and they have all these files free to us use. That's great. Anyway, so now let's see if project builds. And once it builds, we're gonna run it on the board. Now look at that. Project built really nicely. And I'm gonna hook up the board and let's see if those LEDs turn on. All right, I have the board hooked up and I just hit the debug button. So we're gonna go through the code step by step. So that one's good. Now we're actually stepping through the register writes, and it seems like we are writing to the registers. Now next two lines are the ones that will actually turn on the LEDs for us. So here we go. And yes, we do have LEDs. They turned on. Awesome. The LEDs are on. Our code worked. Now we have a clean code. It's more maintainable. It's easier to read. It's more mistake proof. Now we don't have to go and look for every single register offset each time we need to write to a register. We have a header file that has all the structure pointers, and most of all, this saves a lot of time. So in the next lesson, we're going to try to tackle the right side of our code. Ideally, we want to have a GPIO driver. For example, a function that will take in what port we're writing, what pin we're setting, what mode it is going to be in, and speed, etc. So in the next lesson, we're gonna write a GPIO driver, and it'll simplify our code. I'll make it more industry standard, and honestly will help us to write better programs, more complicated programs in the future. So stay tuned for that.